Again, welcome to DSRT 734 class, Inferential Statistics in Decision Making. These lectures cover introduction to probability. So our main objective is to go through the concept of probability, the basic concept. Then we are going to identify the sample space of a probability experiment. We shall also go through some definitions and terminologies related to probability topic. Then we're going to distinguish among classical probability, empirical probability, and subjective probability. From there, we're going to solve some problems, examples. So first, let's start with the definition. What is a random experiment? A random experiment is defined as any activity or a phenomena that meets the following conditions. One, there's only one distinct outcome for each try of the experiment. Two, the outcome of the experiment is uncertain. So this means the result of any experiment we conduct, we cannot predict it. It's uncertain, we don't know it. And also anytime we do an experiment, we should have only one distinct outcome. Then the set of all the distinct outcome of the experiment can be specified and also called a sample space. So a sample space is all the possible distinct outcome of an experiment. For example, tossing a coin. I know if I toss a coin, I have only two possible outcomes. Either we get the tail or we get the head. Now, there's no any third outcome. So the sample space here will be only the head or the tail. Now, the outcome can be either the head or the tail also. So what is an outcome? Here we say an outcome is any member of a sample space. Again, we said the sample space is the total possible distinct outcome of an experiment, like tossing a coin. The total outcome, distinct outcome for tossing a coin is either the head or the tail. So head is one outcome, tail is another outcome. The possible outcome for this experiment, tossing a coin, is head and tail, which is the sample space. Next is an event. So event will be a set of outcomes. So an event is a set of outcomes. And one event is tossing a coin is an event. The outcome of it is either the head or the tail. Next is the relative frequency. Now, if an experiment is performed n times, for example, 5 times, 6 times, here we are assuming n times, under identical conditions. So the condition must be the same. And the event A happens k times, then the relative frequency of A, which is event A, is given by the following expression. So the relative frequency of A will be k over n. So n will be the total number of times the experiment is performed. K will be how many times the event takes it. So we say event A happens k times. So K will be how many times the event happen, the result. So we can see that relative frequency is like finding the proportion of something. We are doing one experiment. And the experiment on the event A, when we do it 10 times, we get 3 times appear out of the 10 times. So it will be 3 over 10. So here we say the relative frequency converges as n increases. Then the relative frequency is said to be probability of A. Again, we're going to see an example soon. Next is the observed relative frequency. So here we have experiment. The experiment here is toss a coin and observe which side of the coin appears on top. Now, the duration of the experiment will be, we are going to toss the coin 1,450 times. So this means n equal to 1,450. Now, observe the event getting ahead. When we toss the coin 1,450, the same coin, 1,450 times, the head occurs 718 times. So what's the probability of having a head when I toss a coin. And that's what we call the relative frequency. So relative frequency of the event getting a head will be K over N. So the number of times we have the head, 718, and how many times we toss the coin is 1450. So the answer here is 0.4952. Or we can say 50% chance of a gain having a head when you toss the coin. Next is the law of large numbers. This is one of the theories in probabilities. As we know, if we are doing some experiment and we keep doing it over and over and again, the system may learn, or whatever we are applying the experiment on the event may learn. So here, for example, we say that as the number of repetitions of an experiment increases, the relative frequency of an event tends to approach the actual probability. And again, we're going to see an example. So next, we start with the classical probability. Now, using the classical approach to probability, the probability of an event A, denoted by P at A, is given by the number of outcomes in A divided by the total number of outcomes in the sample space. So we can say that tossing a coin, and we are looking for the probability of getting head or tail when we toss a coin, is a classical probability, because the probability of getting head will be what? The number of coins the number of outcome that we get head divided by the total number of outcomes in the sample space. So if we toss the coin 500 times and 200 times we have head, the probability of having head will be 200 divided by 500. So here they say we should be very cautious. When using the classical approach, we should always ensure that each outcome in the sample space is equally likely to occur. Is equally likely to occur. So let's see an example now. Here we have a coin. The coin was tossed 3 times, and the number of heads were observed. Now, this is the sample space, consists of 8 outcomes. So these are the possible outcome we can get if we toss a coin 3 times. The first time we toss it, we can get 3 heads. Next time we can get head, head, and tail. Next time we can get head, tail, head, head, tail, HH, etc. is 8. Now, the best way always we can find the total sample space is that I'm tossing a coin 3 times, and the possible outcome is what? 2. So I'm going to raise the base, which is 2, to the power how many times I'm tossing it. So 2 to the power 3 will give me 8. And again, we're going to solve more problem, get the idea. So the sample space always will be the possible outcome, or this, in this case, the possible outcome to the power of how many times something is taking place. Here we are tossing the coin 3 times. The possible outcome is 2. So 2 to the power 3 give me 8. So the sample space, or the total possible outcome, will be 8. Now the question says, let A be the event of getting at least 1 head. What is the probability of A? So here we can see that probability of A will be 7. Why? Because it's only one sample space that we have TTT. Everything is head. I mean, there's only one outcome that everything is a head. So which is the remaining 7 outcomes, at least we have 1 head, or 2 head, or 3 heads. So here we say, since the event A consists of 7 outcomes, H, all the way to TTH, all these 7 outcomes have at least 1 head. And that's what the question said. A coin was tossed 3 times. The number of heads was observed. Let A be the event of getting at least 1 head. What is the probability of A? It will be 7 over. First of all, we have to know how many times at least A will occur. 7 times What is the sample space? 8. So our answer will be probability of A will be 7 divided by 8, which will give us 0.875. Now let's try a second example. Here we roll a die and observe the number of dots on the uppermost surface. Let A be the event observing an event number. What is the probability of A? First of all, we are rolling a die. We should know the total or the sample space, the total outcome. And we know a die have 6 sides. So the total outcome will be 6. 1, 2, 3, 4, 5, 6, 6. Now the question said that what is the probability of A? A means an event of observing even number. Now from 1 to 6, we have even numbers of 2, 4, 6. So this event will be 3. And the sample space will be 6 because a die have 6 sides. So here we say since there are 3 outcomes in A and 6 outcomes in the sample space, the probability of getting A will be 3 divided by 6, which will give me 0.5. Again, this question, the event A is the probability of having even number. And a die have 6 sides from 1, 2, 3, 4, 5, 6. How many even numbers are there? From 1 to 6, how many even numbers we have? We have 3. So it will be 3 divided by 6.5. Now, assuming we have a deck of playing cards, consists of 13 hearts, 13 clubs, 13 spades, and 13 diamonds. Draw a card from a well-shuffled deck and observe the suits of the card. Let A be the event of drawing a heart. What is the probability of A? So here we are looking at what is the probability of getting a heart. And remember here we have 13 hearts, 13 clubs, 13 spades, 13 diamonds. So we should know the total sample space, or I would say the total outcome or the sample space. It will be 52. 13 hearts plus 13 clubs plus 13 spades plus 13 diamonds will give me 52. Now we know we have, what's the probability of drawing heart? We have 13 hearts. So this means probability of A will be 13 over 52, which is 1 over 4 and is 0.25. Since we have 13 hearts and the total cards are 52. Let's try another example. A coin was tossed 3 times and the number of heads was observed. The outcome in this sample space were as follows. We went through this question, but this time we are looking for a different event. So this is the total outcome or the sample space is 8. Now, could the sample space in this experiment have been formulated differently? Also, could, for example, the outcome be defined as the number of heads in 3 tosses? So we have S equal to 0, 1, 2, 3. Now, this is the solution. Using the classical definition of probability requires that the outcome be equally likely. Now, since the sample space S equal to 0, 1, 2, 3 does not contain equally likely events, then here we say the classical definition of probability is not applicable. Because based on the question, we can see, let's go back. This is our coin. We toss it 3 times. The possible outcome, total outcome, or the sample space is 8, which is least here X, uppercase S. But the question was asking, could the sample space in this experiment have been formulated differently? And also could, for example, the outcome be defined as the number of S in 3 tosses when S is 0, 1, 2, 3. Again, it's impossible. So using the classical definition of probability requires that the outcome be equally likely. the outcomes must be equally likely. Now, since the sample space S equal to 0, 1, 2, 3, which was given to us in the question, does not contain equally likely events, the classical definition of probability is not applicable. We can't use it here. Now, that takes us to what is a classical probability and the types of probability. With classical probability, we said that each outcome in a sample space is equally likely. And I think that's the main thing missing in our previous example. Now, that means probability of E will be the number of outcome in event E divided by the number of outcome in sample space, or we say the total outcome in the sample space. And now let's see an example here. We roll a 6-sided die. We want to find the probability of each event. Event A, rolling a 3. Well, rolling a 3, how many 3 we have in a die? Only 1. So it will be, and the side is 6. So it will be 1/6. Now, event B, rolling a 7. There's no 7. We only have 6 sides. So 0. Event C, rolling a number less than 5. Well, a number less than 5 will be 1, 2, 3, 4. So it will be 4/6. Let's look at the solution. First one, we know our sample space. This is a die. So we have 1, 2, 3, 4, 5, 6, as we can see the images. Then event A, how do we roll a 3? The probability of rolling 3. Very simple, only 1 will count. So it's 1/6. Now question 2, 7. The 7 is not in the sample space. We don't have no 7. So the probability of getting 7 is totally 0. Now, C said roll a number less than 5, which means we can get 1, 2, 3, 4. So it will be 4/6. That will give us 0.667. Next is the empirical probability. Now, empirical probability, that's why it's called empirical. Again, it's based on some previous event or observation. So here we say based on observation obtained from probability experiment. Based on observations that obtained from probability experiment. So the relative frequency of an event. So probability of E is the frequency of event E divided by the total frequency. So let's see an example here. A company is conducting an online survey of randomly selected individuals to determine if traffic congestion is a problem in their community. So far, we have 320 people have responded to the survey. What is the probability that the next person that responds to the survey says the traffic congestion is a serious problem in their community? So this is our response, 320. The serious problem is 123. Moderate problem is 115. Not a problem is 82. So, for example, the probability that there will be a response that not a problem, it will be 82/320. The probability that is moderate problem is 115/320. Probability that is a serious problem will be 123/320. Now the question says, what is the probability that next person that responds to the survey says the traffic congestion is serious problem? So that will be 123. Now you can see this is empirical probability based on the previous result, because the previous response, we have 123 out of 320 saying traffic congestion is a serious problem. So the question says, what will be the next, that's the next in the future, the next person that respond. So this is not classical. Classical is based on relative frequency, part of the whole. So the answer again will be 1, 2, 3, that's the event, over 320, the total response. So we can say that there's 38.4% that the next response will say traffic congestion is a serious problem. Next, we go to the subjective probability. Actually, this is why it's called subjective subject. not objective, subjective probability. So subjective probability means it's based on some belief, some condition, some phenomena. So here example, they say intuition, based on intuition, or educated guess, or approximate, we can estimate. So example here, doctor may feel a patient has 90% chance of full recovery. This is not based on previous events, but based on the doctor's intuition, educated guess. So classify the statement as an example of classical, empirical, or subjective probability. Let's see if we can distinguish between all those three probabilities. The first question, the probability that you will be married by age 30 is 0.50, which we will say 50%. Probability that you will get married by the age of 30. So it's based on an educated guess or my intuition. So this is a subjective probability, most likely an educated guess. We don't have previous data or finding the relative frequency to come up with some probability value. Second question, the probability that a voter chosen at random will vote Republican is 0.45. The keyword here is random. Random. So this will be empirical probability, most likely based on a survey. The probability that a voter chosen at random will vote Republican. Now, the probability of winning 1,000 ticket raffle with one ticket is 1/1,000. This is again classical probability. I would say it's based on proportion or relative frequency. So this will be a classical probability, equally likely outcome. Next, we talk about stat inference. Again, we will get more data on this topic from chapter 8 of our course textbook. And here we say stat inference is involved the use of sample data to form generalization or inferences about a population. So example, using the sample data to estimate the value of population parameters is one form of stat inference. And this concept comes to example, hypothesis testing. We may cover different types of hypothesis testing, both for parametric and non-parametric, such as sign tests, even regression, Spearman correlation, PSC correlation. PSC correlation is for quantitative data, whereas Spearman correlation is for qualitative, or we will say the ordinal data based on ranking. And we may get more data. Actually, statistics and inferential, we will say inferential statistics is the main foundation of this course. Now we start with the descriptive. We completed with descriptive. We will go through probability now. After probability, most of the materials in this course will cover inferential statistics. So again, wish everybody the best and thank you.